At -50 degrees Celsius, an uninsulated steel axe blade will shatter like brittle glass if dropped on stone. Yet human beings survived for thousands of years inside houses built out of frozen water. To understand how that is physically possible, you have to stand on the open ice of the Canadian Arctic archipelago in the middle of November. Out here on the vast white expanse of the Baffin Territory, there are no forests to harvest for timber, no clay to bake into bricks, no stone exposed beneath the miles of glacial pack, and no iron ore to forge into armor against the weather. When the sun dips below the horizon for its months-long winter absence, the horizon is swallowed by a freezing mist that turns the sky into an endless gray wall. The air does not merely feel cold. It acts as an active physical force, slicing through woven wool and driving straight into human lung tissue. Temperatures regularly plummet past -50 degrees Celsius, accompanied by howling Arctic gales that sweep across the flat tundra at 60 miles per hour, capable of ripping unsecured canvas to shreds in minutes. Yet, if you were standing on that frozen plain in November of 1888, you would have witnessed a scene so visually contradictory that it defied every rule of European engineering. On one side of a low snow ridge stood the temporary camp of a British polar expedition led by Lieutenant Arthur Hayes. His men were huddled inside thick, double-walled canvas tents, reinforced with iron poles and fueled by heavy cast-iron coal stoves. Despite the roaring fires and piles of wool blankets, the men were shivering violently, their breath freezing into thick crusts of frost on the canvas ceilings, while their boots froze solid to the muddy ice beneath their feet. Fewer than 100 yards away, sitting directly on the open, wind-blasted snowpack, was a smooth, rounded dome constructed entirely out of blocks of frozen snow. Inside that white dome, an Inuk master builder named Auka and his family sat in shirt-sleeve comfort. They were resting on an elevated snow platform covered in caribou skins, sipping hot seal broth, chatting quietly, and tending a small stone lamp. The air around them was a stable, comfortable 15 degrees Celsius above zero. Outside, the killing gale roared at -52 degrees. Inside, the family lived in a gentle, warm microclimate that maintained a mind-boggling temperature differential of 67 degrees Celsius higher than the environment outside. How could a shelter constructed out of the very material that threatens to freeze a human being to death hold more heat than a military-grade canvas tent with a coal-burning stove? How could a structure built without a single piece of wood, stone, mortar, or steel withstand 90-mile-per-hour winds without collapsing, while keeping its interior dry, bright, and completely warm? The answer lies in a masterclass of structural physics, fluid dynamics, and thermodynamics that was perfected over thousands of years by indigenous northern builders. The snow dome, or Igluvigaq, was never just a temporary shelter against the wind. It was a high-performance, self-healing, biothermal survival machine engineered out of the only resource the landscape provided. Before we break down the exact physics of how this snow architecture achieved the impossible, take a moment to drop a comment below letting us know where you are watching from today and tell us the coldest winter temperature you have ever personally survived. And if you love deep dives into forgotten historical survival engineering, make sure to hit that subscribe button to support our channel so you never miss an episode. Now, let us look at the catastrophic mistake European explorers kept making when they tried to fight the Arctic with metal and canvas, and why their advanced technology almost got them killed. Lieutenant Arthur Hayes was a man who believed in the absolute superiority of Victorian industrial science. He had arrived in the Baffin Territory equipped with the absolute finest gear the British Royal Navy could buy. His expedition carried double-walled canvas tents lined with oiled sailcloth, heavy cast-iron stoves designed to burn high-calorie Welsh coal, rubberized ground sheets engineered to block moisture, and thick, multi-layered wool uniforms. Hayes viewed the Arctic as an enemy, to be conquered through force of iron and fuel. When he first encountered Auka and his family, Hayes looked at the native snow structures with polite condescension, referring to them in his official journal as barbaric ice caves that were unsuitable for civilized men. Within 48 hours of setting up camp on the open tundra, Hayes's industrial technology began to betray him in ways he had never anticipated. The first failure was thermal bridging. The expedition's canvas tents were held up by rigid iron support poles and anchored with steel pegs driven into the frozen earth. In thermal physics, metal acts as an extraordinarily high-speed conductor. Rather than insulating the interior, the iron poles acted as thermal highways, drawing the small amount of heat produced by the coal stove directly out through the roof and venting it into the freezing sky. Every point where metal touched the tent fabric created a localized zone of extreme cold, causing the interior moisture from the men's breath to condense and freeze into thick, jagged icicles. The second failure was the canvas itself. While canvas blocks wind when dry, it possesses zero thermal resistance value. Worse still, human beings produce a tremendous amount of water vapor simply by breathing and sweating, nearly 2 pounds of water per person every single day. In the sealed canvas tents, this warm moisture rose toward the ceiling, met the freezing fabric, and instantly transformed into a dense layer of indoor frost. Whenever the wind shook the tent walls, this frost rained down on the sleeping officers, soaking their wool blankets. In sub-zero conditions, wet insulation loses all its ability to trap air, meaning the blankets became useless sheets of damp lead. The third and most dangerous failure occurred at floor level. Hayes had instructed his men to set up their iron coal stoves directly on the rubberized ground sheets over the snow. As the coal stoves burned, they radiated intense heat downward. But instead of warming the tent air, that heat melted the permafrost directly beneath the floor, creating a muddy pool of freezing slush. When the stoves eventually burned down in the middle of the night, that slush refroze into a flat sheet of solid ice, locking the men's equipment into the floor and drawing body heat directly out of their sleeping bodies through conductive contact. Within a week, Hayes's expedition was in severe crisis. They were burning through their precious coal reserves at 3 times the calculated rate just to keep the interior tent temperatures slightly above freezing. The men were exhausted, suffering from stage 1 frostbite on their toes and fingers, and coughing constantly from the acrid coal smoke trapped inside the damp canvas enclosures. Hayes had brought tons of fuel, iron, and canvas into the Arctic, yet his men were freezing to death. He had treated the environment as an adversary to be repelled by heavy physical barriers. He did not understand that in extreme polar conditions, trying to force brute force heating into an uninsulated, high-conductive structure is a battle you will always lose. Auka, standing outside his quiet snow dome, watched the British sailors struggle with their smoking stoves and frostbitten gear. He knew that the Englishmen were fighting the cold with raw force, whereas the secret to surviving the Arctic was not fighting the cold at all. It was understanding the hidden physical properties of the snow itself and transforming the frozen landscape into a living shield. As the barometric pressure began a steady, alarming drop on the morning of November 14th, Auka stood on a high ridge overlooking the frozen inlet. The sun was surrounded by a pale, milky halo, a classic atmospheric indicator that a massive polar vortex was gathering strength to the north. Auka knew that within 24 hours, an Arctic gale would sweep across the territory, bringing temperatures well below -55 degrees Celsius and wind speeds that would flatten any conventional shelter. If Lieutenant Hayes and his crew remained inside their failing canvas tents, they would not survive the week. Auka decided it was time to build a master snow dome, an Igluvigaq, large enough to shelter both his family and the stranded British officers. To build a high-performance snow structure that can withstand a polar vortex, the builder must first become a master of material physics. To an outsider, snow is simply frozen water, a cold, uniform white powder. To an Inuk builder, snow is an incredibly complex material with hundreds of distinct structural classifications, each possessing radically different density, shear strength, and thermal properties. If you try to build an igloo out of soft, freshly fallen powder, the structure will immediately collapse under its own weight because loose snowflake crystals contain too much unbonded space to support a structural arch. Conversely, if you try to carve blocks out of solid blue sea ice, you create a thermal disaster. Solid ice is dense and lacks air pockets, meaning it conducts heat 80 times faster than trapped air. A house made of solid ice acts as a giant cold sink, drawing body heat straight out of a human being until hypothermia sets in. The material an Inuk builder looks for is called Pukangajuk wind-packed snow. Pukangajuk is not formed by gravity or simple settling. It is created when fierce, sub-zero Arctic winds scour the open plains, picking up loose ice crystals, breaking off their delicate branches, and slamming them together at high velocity until they interlock into a dense, compressed, homogeneous matrix. This wind-driven mechanical hammering creates a material that represents a brilliant thermal paradox. It is structural enough to be carved into sharp, load-bearing bricks that can support the weight of a full-grown man standing on top of them, yet it remains filled with millions of microscopic, trapped air pockets. These air pockets turn the dense snow block into a world-class natural insulator, creating a material that resists heat transfer almost as effectively as modern specialized foam paneling. To locate the exact drift of Pukangajuk hidden beneath the vast white landscape, Auka used a specialized testing instrument called a sabagut, a thin, flexible probe crafted from smoothed reindeer antler attached to a wooden handle. The physics of using the sabagut are precise and tactile. Auka walked across the drifts, thrusting the antler probe deep into the snowpack at varying angles to feel the resistance beneath the surface. If the probe glided through the snow with little effort, the snow was too soft and powdery, indicating a weak internal crystal bond that would fracture under load. If the probe struck an impenetrable barrier or required immense force to drive forward, he had hit a layer of solid ice or refrozen slush, which would bleed heat and shatter when carved. Auka was searching for the precise Goldilocks zone of resistance, a uniform, firm rebound that felt like pushing a blade through dense, cold butter. When the probe encountered this specific density, it meant the wind had packed the snow crystals evenly throughout the entire depth of the drift, ensuring that every block carved from this location would possess identical strength and thermal resistance. Beyond tactile feedback, Auka used acoustic testing to verify the structural integrity of the snowpack. He tapped the side of his long snow knife against the frozen drift and listened intently to the sound that echoed through the snow. A soft, dull thud meant loose powder beneath. A sharp, metallic ringing indicated brittle ice, but when the snow produced a distinct, high-pitched, screech-scratch resonance, Auka knew the crystal matrix was in perfect mechanical equilibrium. The interlocked ice grains were bound tightly enough to distribute structural loads without fracturing, yet porous enough to trap the static air required for high-grade insulation. He had found his white gold. Now, the extraction process could begin. With the ideal snowpack identified, Auka pulled his primary tool from his belt, the pana, or snow knife. The pana is a masterwork of functional tool design, historically crafted from the split rib bone of a bowhead whale or carved from walrus ivory. Auka's blade was forged from a piece of salvaged ship steel, ground flat, and fitted with an extended wooden antler handle. The blade was long, straight, and double-edged, designed specifically to make deep, perfectly vertical shear cuts through compressed snow without tearing the delicate crystal matrix. The long handle allowed for a wide, two-handed grip, giving the builder massive leverage even while wearing thick, double-layered caribou mitts. Auka did not use manufactured rulers or metal measuring tapes to lay out his structural dimensions. Instead, he relied on an ancient, highly standardized system of anthropometric measurement based on his own body. He used the distance from his elbow to his fingertips, a historical unit known across many cultures as the cubit, to determine the precise length, width, and depth of the snow blocks he was about to carve. By using his own limbs as a constant measuring standard, Auka ensured that every single block carved from the drift would maintain identical geometric proportions, allowing them to interlock with mathematical precision during construction. The extraction process followed a clever, highly efficient circular logistics strategy. Auka did not cut snow blocks far away and haul them across the ice to his building site. That would waste precious human calories and slow down construction. Instead, he carved his building blocks directly from the snowpack inside the perimeter circle of the planned dome. Auka began by using his pana to carve an initial, large X into the wind-packed surface of the drift to establish a clean starting edge. He then sliced two long parallel vertical lines roughly 30 centimeters deep into the snow, using his forearm to gauge the distance. Next, he made a deep undercut beneath the base of the block. With a series of quick, controlled rhythmic jabs at the bottom edge, the snow block popped out cleanly along its natural horizontal cleavage planes. Each extracted block was a massive, clean-edged rectangle, measuring roughly 80 centimeters long, 40 centimeters high, and 20 centimeters thick, weighing between 20 and 40 kilograms. Because the snow was dense, Pukangajuk, these heavy blocks could be lifted, rotated, and handled without crumbling. As Auka systematically carved block after block from within the footprint of his floor plan, something remarkable happened. By extracting his building materials directly from the floor, he was simultaneously excavating a deep, circular pit in the ground beneath the future dome. This was not an accidental side effect of digging. It was a critical piece of thermodynamic floor engineering, known as the cold sump. In the physics of fluid dynamics, cold air is significantly denser and heavier than warm air. Warm air expands, becomes buoyant, and rises toward the ceiling, while cold air contracts, settles, and pools at the lowest available point in an enclosed space. By digging the interior floor down nearly a full meter below the surrounding snowpack, Auka created a physical trap for freezing air. Any cold drafts that entered the structure, along with the heavy cold air generated inside the dome, would naturally slide down off the living surfaces and sink into this lower floor trench. This simple act of interior excavation meant that the living and sleeping areas could be constructed on a raised shelf above the cold pit, placing the inhabitants comfortably inside the upper warm air zone of the shelter without requiring a single extra block of snow to achieve vertical headroom. With his materials carved and his cold sump established, Auka was ready to assemble the dome. Lieutenant Hayes, standing at the edge of the pit, wrapped in his heavy wool coat, watched Auka lay the first circle of snow blocks around the perimeter of the excavated trench. Hayes shook his head in disbelief. To the British officer, who was trained in brick masonry and wood framing, what Auka was attempting looked structurally impossible. Hayes knew that if you stack heavy blocks in a circle and begin leaning them inward to form a roof, the leaning top blocks will simply fall inward and collapse under the pull of gravity, unless you build a temporary timber frame or wooden scaffolding underneath to support them while the mortar sets. Since there was not a single stick of wood on the tundra, Hayes assumed the dome would collapse the moment the walls began to tilt. What Hayes did not understand was that Auka was not building in horizontal rings. He was utilizing a self-supporting, continuous spiral. If you stack snow blocks in flat, parallel horizontal rings, each ring remains an isolated layer. When you attempt to lean the second or third ring inward toward the center, gravity pulls the unsupported blocks straight down into the room. To eliminate this structural instability, Auka took his panna after placing the very first ground ring of blocks and made a dramatic, sloping cut. Starting from the top edge of the first block, he sliced diagonally downward at a 15-degree angle across the next two blocks until his blade touched the floor. This single diagonal cut transformed the flat base into a continuous, ascending spiral ramp. Now, when Auka placed the next block on top of the ramp, the block was no longer sitting on a flat, unstable horizontal seam. Instead, it rested on a rising incline, supported simultaneously by two distinct contact surfaces: the sloped surface beneath its base and the vertical side, face of the preceding block in the spiral. This dual contact geometry completely changed how physical forces acted on the snow. As Auka added block after block along the rising spiral, the weight of each new block leaned inward toward the center of the room. But instead of falling, the block pushed sideways against the preceding block in the spiral, transferring its weight laterally along the ascending arch. The more the walls tilted inward, the tighter the blocks squeezed against one another. Gravity, which normally pulls buildings down, was being redirected sideways, wedging the interlocked snow blocks into a self-supporting structural loop that grew stronger with every block added. As each block was settled into its position along the spiral, Auka delivered a firm, practice strike to its exterior face with the flat palm of his heavy mitten, a technique known as centering or delivering the knowing thump. To an observer, This looked like a simple tap to adjust the alignment. In reality, it was a brilliant application of thermodynamic friction welding. When Auka struck the dense snow block, the kinetic energy of the impact generated an instantaneous rise in friction temperature at the microscopic contact points where the ice crystals of the two blocks touched. This brief friction spike melted a microscopic layer of ice crystals on the block surfaces. Because the surrounding air and snow were far below freezing, this microscopic film of liquid water refrozen instantly the millisecond the pressure ceased. The two separate snow blocks were instantly ice-welded together into a single, seamless, monolithic mass. Through this friction welding process, the igloo ceased to be a fragile stack of individual snow bricks. It was rapidly becoming a unified, high-strength shell of continuous, interlocked ice-armored snow. As the spiral walls climbed higher, curving gracefully inward toward the center, the angle of the lean became extreme. The blocks near the upper third of the structure were tilted at nearly 60 degrees off the vertical axis, hanging suspended over the open pit below. Yet, due to the continuous spiral geometry and the instant friction welding of the surfaces, not a single block slipped or fell. The overall shape Auka was building was not a simple, round hemisphere. It was an inverted parabola, a mathematical curve known in architectural engineering as a catenary arch. In structural mechanics, a catenary arch is the precise shape formed by a hanging chain allowed to sag under its own weight when supported at both ends. When you invert that exact curve upward to form a three-dimensional dome, a profound physical transformation occurs. Every single internal force acting on the structure is converted into pure compression. In standard rectangular buildings, roofs and walls are constantly subjected to tension and shear forces that pull materials apart or bend them sideways. Snow and ice have extremely low tensile strength. If you pull on a snow block or bend it, it snaps instantly. But snow has remarkably high compressive strength when pushed together. By utilizing the inverted catenary arch geometry, Auka ensured that there was zero tension or bending force anywhere in the dome. The entire dead load of the heavy snow blocks was directed along smooth, descending compression vectors, straight down through the walls and into the solid frozen ground beneath. Now, only one final, critical hurdle remained: closing the open hole at the very apex of the dome. This hole, measuring roughly 50 centimeters across, was the most structurally vulnerable point in the build. If this final gap was not closed correctly, the entire upper section of the inward-leaning spiral would lose its lateral support and cave inward. To seal the crown, Auka carved a highly specialized custom piece known as the king block. The king block was a massive, wedge-shaped key block cut, specifically with a pronounced bevel. Its top face was noticeably wider than its bottom face, forming a truncated, inverted pyramid. Installing the king block required a high-precision, blind structural maneuver. Auka stood inside the dark, almost completed dome, holding the heavy king block in his mittened hands. Working entirely from the inside, he lifted the block up through the open apex hole, passing it completely outside the building into the open air. Then, holding the block suspended above the roof from below, he rotated it 90 degrees horizontally in mid-air. Finally, he carefully lowered the wedge-shaped block back down into the opening from above, drawing it tight into the tapered gap like a heavy mechanical cork. The moment the wedged king block settled into place, the structural circuit was closed. The wedge shape of the key block prevented it from falling through the opening, while its heavy downward weight pushed outward against the top edges of the surrounding sloped wall blocks. This created an intense, continuous, outward and downward compressive force that locked the entire upper arch into place. The inverted catenary geometry was now fully energized. The structure ceased to be a collection of leaning blocks and became an indestructible, rigid shell. To demonstrate the absolute stability of the engineering to the watching British officers, Auka climbed up out of the entrance pit, walked up the exterior curve of the dome, and stood directly on the very apex of the snow roof. The thin, hand-carved snow shell supported his full body weight without settling, creaking, or shifting a single millimeter. Gravity had been completely transformed from a threat into a structural asset. Just as Auka stepped down from the roof of the completed dome, the horizon vanished. The heralds of the polar vortex had arrived. The atmospheric pressure plummeted to a terrifying low, and within 45 minutes, the winds roared down from the polar ice cap, accelerating to a sustained 65 miles per hour with gusts exceeding 80. The air temperature crashed to minus 55 degrees Celsius. With the severe wind chill factored in, the environment dropped to an equivalent minus 75 degrees. Exposure to that level of cold would freeze human lung tissue in under 4 breaths and cause irreversible stage 3 frostbite to exposed skin in less than 30 seconds. Before retreating inside, Auka's family applied the final protective layer to the exterior of the dome, a process known as applying the shack sack. While Auka had been building the main structure, his wife and eldest son used small wooden shovels to throw fine, loose, light-powdered snow over the entire outer surface of the dome, completely burying the carved blocks under a soft, 3-foot-deep blanket of loose powder. This was not done for aesthetic reasons. It was a deliberate application of thermal sintering physics. When fine, loose snow powder is thrown against a solid, cold surface, the microscopic air spaces between the loose flakes act as an additional layer of supreme thermal insulation. But as the interior of the dome began to warm up from human metabolic heat, a dramatic temperature gradient was established across the thickness of the walls. The inside face of the snow blocks was exposed to warmth, while the exterior face was exposed to minus 55 degrees. This massive 50-degree temperature differential across the wall created a continuous vapor migration process through the porous snow matrix. The fine, loose, shack sack powder on the outside began to sinter its delicate crystals fused together, filling every microscopic crack, seam, and gap between the carved blocks. The shack sack transformed the igloo into a living, self-healing armor. Unlike a wooden or metal building, which is gradually degraded and weakened by wind pressure, the snow dome actually grew stronger as the storm raged. The gale-force winds blasted fine snow against the exterior, where it packed tightly into any tiny surface imperfections, sealing the shell even further. The harder the Arctic wind blew, the tighter the outer armor was packed, creating a completely windproof, zero-leakage thermal envelope that was entirely immune to wind-driven convective heat loss. Meanwhile, less than 100 yards away, Lieutenant Hayes's camp was being torn to pieces. The 80-mile-per-hour gusts caught the flat, vertical surfaces of the British canvas tents, causing the fabric to whip violently until the seams ripped apart. The iron support poles snapped or bent under the wind load, collapsing the heavy frost-covered canvas directly onto the sleeping sailors. The coal stoves were snuffed out as the chimneys backdrafted, filling the collapsing tents with blinding, suffocating smoke. Fearing for their lives as hypothermia set in, Hayes and his frozen men abandoned their ruined equipment and stumbled blindly through the roaring whiteout toward the steady silhouette of Auka's snow dome. Guided through the blinding storm by a leather lifeline Auka had anchored between the camps, the freezing British officers reached the external entrance of the igloo. Here, they encountered the final piece of exterior fluid dynamic engineering, the 3-meter baffled entrance tunnel. Auka had not cut a simple door in the side of the dome. To enter the igloo, one had to drop down into a low, sunken trench dug 3 meters outside the building, crawl through a narrow, curving underground snow tunnel, navigate a sharp 90-degree turn, and then ascend upward through the floor pit into the main room. This winding subterranean entry functioned as a perfect fluid dynamic airlock. When the 80-mile-per-hour gale roared across the tundra, the horizontal wind could not penetrate the sunken, curving tunnel. The heavy, freezing exterior air was trapped at the bottom of the sunken entry pit, unable to rise against gravity into the elevated living space above. The 90-degree turn killed any remaining wind velocity, ensuring that when Hayes and his shivering men crawled up out of the floor pit into the main room, they stepped into a dead-silent, completely draft-free environment where the air was stationary, calm, and astonishingly warm. As the rescued British officers lay on the floor of the entrance trench, recovering from the sheer physical shock of escaping the killing gale, they began to realize that the igloo was not an isolated shelter. It was merely the central hub of a vast, highly sophisticated survival ecosystem that allowed the Inuit to thrive in an environment that killed unadapted outsiders. While the storm raged outside, Auka's son Nuka brought their working equipment inside the wide storage alcoves carved into the sides of the entry tunnel. Among this gear was their primary transport vehicle, the Kamutik, or Arctic sled. The Kamutik is a masterpiece of materials engineering, designed to solve a problem that crippled European transport. In extreme sub-zero temperatures, rigid materials like steel, iron, and dry timber become extremely brittle and snap when subjected to sudden mechanical impacts. A traditional European wooden sled, held together by rigid iron bolts and nails, would shatter its joints when hauled over jagged, uneven pressure ridges of sea ice at high speeds. The Inuit solved this by completely eliminating rigid fasteners. The crossbeams of the Kamutik were bound to the long wooden or bone runners using flexible lashings made of braided seal-hide thongs. This soft joint construction allowed the entire sled frame to twist, flex, and snake over jagged ice obstacles like a living organism. When the sled struck a sharp ice ridge at speed, the kinetic energy of the impact was absorbed and distributed throughout dozens of flexible leather joints, rather than concentrating at a single rigid stress point. The sled could bend up to 20 degrees out of alignment without breaking a single component. To solve the issue of friction on dry, abrasive Arctic snow, which, at -50 degrees, acts exactly like coarse sandpaper against wooden runners, the Inuit engineered a surface coating known as runner mud. Nuka had prepared the runners earlier that season by mixing decomposed tundra peat moss with warm water to form a thick, smooth paste. He applied this paste evenly along the bottom of the runners, shaping it by hand into a smooth, rounded profile, and allowed it to freeze solid. Once frozen, he scraped the mud surface flat with his snow knife and sprayed a fine mist of warm water over the frozen peat using his mouth. The water froze instantly upon contact, forming a glass-smooth, ultra-frictionless coating of pure ice over the peat base. This ice-on-ice gliding surface reduced mechanical friction to near zero, allowing a dog team or a single hunter to haul a multi-hundred-kilogram load across the dry snowpack with minimal physical effort. Next, Hayes looked at the clothing Auka and his family were wearing. While the British sailors wore heavy, multi-layered uniforms made of dense wool and heavy oilskin coats, which had absorbed sweat, frozen stiff, and provided zero warmth. Once wet, the Inuit wore double-layered suits carved from caribou skin. Caribou fur is the most effective biological insulation material on Earth. Unlike the solid hair shafts of sheep wool or human hair, every individual caribou hair is a hollow cylinder filled with a microscopic, cellular honeycomb structure of trapped static air. Millions of these hollow hairs trap a massive layer of dead air around the human body, providing an insulation value that far exceeds even the highest-grade modern synthetic fabrics. The parka was constructed in two distinct layers. The inner layer was worn with the hollow fur facing inward directly against the human skin, trapping metabolic body heat at its source. The outer layer was worn with the fur facing outward toward the weather, repelling wind and shedding blowing snow. The true genius of the garment, however, lay in its stitching technology. Inuit seamstresses did not use cotton or linen thread to sew garments, as plant fibers snap in deep cold and wick moisture into seams. They used sinew-dried, split-tendon fibers harvested from the legs and spine of caribou. Sinew is a highly hygroscopic, biological material. It possesses the unique physical property of expanding when exposed to moisture. Whenever a hunter worked hard and began to produce sweat, or whenever sea spray struck the garment, the sinew thread inside the seam would instantly absorb that moisture and swell up, automatically plugging every microscopic needle hole in the skin suit. It was a self-sealing, dynamic, waterproof raincoat that made the clothing completely windproof and impervious to moisture infiltration in conditions that would freeze a modern hiker to death. Finally, there was the problem of internal fuel. To maintain a body core temperature of 37 degrees Celsius in an environment at -50, the human metabolic engine must burn immense quantities of calories. In a landscape devoid of plants, agriculture, or sunlight for 6 months of the year. Obtaining high-energy fuel and essential vitamins is a massive biological challenge. To survive, the Inuit developed advanced techniques of food microbiology and anaerobic fermentation processes that created high-energy biological batteries known as Igunaq and Kiviak. During the brief summer months, hunters would harvest small seabirds, known as little auks, by the hundreds. They would take a whole, fresh seal skin, leave the thick layer of blubber attached to the inside of the hide, and pack 300 to 500 whole birds into the seal bag, feathers, beaks, and all. They pressed all the air out of the bag, sealed the opening with a thick layer of fat to block all oxygen, and buried the seal skin under heavy rocks deep in the tundra permafrost. For 18 months, the package remained buried in the cool earth, undergoing slow, anaerobic fermentation driven by the natural enzymes inside the birds' bodies. The fat layer prevented oxidation and rot, while the controlled enzymatic breakdown pre-digested the dense protein and fat, converting it into a soft, highly bioavailable, cream-like substance. When dug up in the dead of winter, Kiviak provided an extraordinary nutritional battery. It was packed with concentrated fats, pre-digested proteins, active gut probiotics, and massive doses of vitamin D and B complex nutrients that are completely destroyed by cooking and are otherwise impossible to find in a world without plants. Eating a few ounces of fermented Kiviak triggered an immediate, powerful thermogenic response in the human body. The liver processed the pre-digested fats rapidly, ramping up metabolic heat production from within. While Hayes and his men had been starving on dry Navy biscuits and canned salt beef, which required vast amounts of metabolic energy just to break down Auka's family, were fueling their internal fires with ancestral chemical reactors that kept their blood hot and their immune systems invincible. By the morning of the second day of the blizzard, the interior of Auka's igloo had settled into a state of total thermodynamic equilibrium. Lieutenant Hayes and his meteorologist, Dr. Caleb Wright, pulled themselves up off the sunken entrance floor and stepped onto the elevated sleeping platform, known as the igloo. The moment they stepped up onto this raised snow bench, which occupied the rear two-thirds of the dome and stood 50 centimeters above the floor trench, they entered what atmospheric scientists now refer to as the thermal bubble. Because Auka had dug the central floor pit down and raised the sleeping bench up, the occupants were positioned entirely within the upper warm air reservoir trapped at the peak of the catenary arch. At the center of the middle working tier sat the primary heat source of the igloo, the kulak. The kulak was a heavy, crescent-shaped lamp carved from soft soapstone, filled with rendered seal blubber fat. The wick was crafted from dried Arctic cotton grass and fine moss, carefully laid out along the curved edge of the stone trough. Auka's wife managed the lamp using a small bone tool called a takuti. With precise, gentle movements, she trimmed the charred moss wick, maintaining a low, steady, bright blue flame along the entire length of the stone lip. The physics of the kulak were astonishingly precise. The blue flame produced a completely smokeless, odorless combustion that generated roughly 300 watts of continuous radiant heat, just enough energy to warm the elevated living zone without producing excessive heat that would melt the structural snow shell overhead. This steady, gentle heat source had triggered a critical physical surface transformation inside the dome, the ice glazing effect. When the kulak was first lit, the immediate air temperature near the top of the arch rose slightly above 0 degrees Celsius. This caused the innermost surface of the carved snow blocks to melt just a fraction of a millimeter. But as this thin film of liquid water formed, the extreme cold from the outside wall immediately drew the heat away, causing the water to refreeze instantly into a glass, smooth, crystal-clear sheet of solid ice that coated the entire interior surface of the dome. This thin ice glaze acted as an airtight seal and an infrared thermal battery. First, the ice sheet sealed every remaining microscopic pore in the snow, making the dome completely airtight and preventing warm air from leaking out through the walls. Second, the smooth, glassy ice face acted as an infrared mirror. When the occupants sat on the caribou skin platform, the radiant metabolic heat emitted by their bodies struck the ice-glazed walls and was bounced straight back into the center of the room rather than being absorbed into the snow. To prevent any stray moisture drops from dripping down onto the sleeping area, Auka had suspended a thin skin lining made of dehaired seal hides a few inches below the ceiling arch using bone pegs driven into the snow seams. This created a double-layered thermal break, a dead air space between the hide skin and the ice-glazed wall that stopped warm human breath from touching the cold ceiling directly. Light flooded into the warm room through a unique architectural feature, the ice lens window. Directly above the entrance tunnel, set into the southern wall of the dome, was a crystal-clear slab of ice. Auka had not used saltwater sea ice for this window, as sea ice contains trapped salt pockets that make it cloudy and opaque. He had harvested a block of pure, freshwater ice from a deep inland lake early in the season, carved it smooth, and fitted it flush into the snow wall. The clear lake ice acted as a double-paned window, flooding the interior with bright, serene, azure daylight, while maintaining a seal that blocked the 70-mile-per-hour wind outside. Dr. Caleb Wright, the expedition surgeon, could contain his scientific curiosity no longer. He pulled a heavy brass casing from his inner coat pocket and retrieved an official, calibrated Royal Society spirit thermometer, an instrument filled with alcohol rather than mercury, as mercury freezes solid at -39 degrees. Wright stepped to the edge of the elevated platform, held the thermometer at eye level, and waited 3 minutes for the alcohol column to stabilize. He looked at the glass tube, blinked in total disbelief, wiped his eyes, and looked again. The interior air temperature on the elevated sleeping platform read +14 degrees Celsius, 57 degrees Fahrenheit. Dr. Wright then attached the thermometer to a long leather cord, lowered it down into the sunken, cold-sump trench near the entrance tunnel, and waited another 3 minutes. The column dropped instantly, reading +2 degrees Celsius at the bottom of the pit. Finally, Wright wrapped his face, stepped briefly out through the subterranean entry tunnel into the screaming fury of the polar vortex, and held the instrument out into the open gale. The spirit column crashed down the tube, bottoming out at -52 degrees Celsius, -61 degrees Fahrenheit. Dr. Wright climbed back into the warm, quiet dome, his hands trembling as he recorded the data in his leather-filled logbook. The exterior gale air temperature read -52 degrees Celsius. The sunken floor, cold sump temperature read +2 degrees Celsius. The elevated living platform temperature read +14 degrees Celsius. That meant the total passive temperature differential was 66 degrees Celsius. The measurements were irrefutable. Without a single stick of wood, without a single lump of coal, without metal, mortar, canvas, or modern insulation, this simple dome constructed entirely of wind-packed snow had established and maintained a temperature difference of 66 degrees Celsius above the killing environment outside. It was performing with a thermal efficiency that outperformed every military tent, wooden cabin, and brick structure in the Northern Hemisphere. Lieutenant Arthur Hayes stood on the raised caribou platform in his unbuttoned uniform jacket, feeling the gentle, radiant warmth reflecting off the glazed ice walls. He looked at the data in Wright's notebook, looked at the quiet, smokeless blue flame of the soapstone lamp, and then looked at Auka, who was calmly carving a piece of dried meat for his children. The proud British officer, who had come to the Arctic, convinced that iron, coal, and Western science were the pinnacle of human achievement, realized he was standing inside an architectural masterpiece that dwarfed his technology in every conceivable metric. Hayes looked at the Inuk builder, bowed his head, and surrendered his pride to the timeless genius of the North. Sitting together on the raised caribou platform, as the gale howled uselessly against the snowshell above, the boundaries between two different worlds melted away. Auka passed a wooden bowl of warm broth and tender meat to Lieutenant Hayes and his shivering men, as the rich, hot food restored warmth to the sailors' exhausted bodies. Hayes reached out and clasped Auka's hand in a silent, profound gesture of gratitude. There were no speech-making moments or grand declarations, only the deep, universal human understanding that they were alive because an ancient culture had looked at an unforgiving desert of ice and seen not a wasteland to be fought, but a home to be understood. Auka accepted the gesture with the quiet humility that defines the spirit of the North. He explained softly that the Arctic does not yield to force, anger, or heavy materials. To survive where trees cannot grow, a person must learn to listen to the wind, understand the language of the snow crystals, and build in total harmony with the unyielding physical laws of the universe. True strength lay not in imposing one's will upon the earth, but in having the wisdom to adapt to its rhythm. When the polar vortex finally cleared 3 days later, revealing a bright, calm sky, Hayes and his surviving crew emerged from the snow dome as changed men. They helped Auka load his Kamutik sled, sharing their remaining iron tools as gifts of lifelong friendship before beginning their long journey back to the coast. Upon their return to London the following year, Lieutenant Hayes and Dr. Caleb Wright presented their official findings before a packed auditorium at the Royal Geographical Society. Their detailed thermodynamic charts and architectural diagrams of the Igluvigaq shocked the Victorian scientific establishment, forever dismantling the arrogant myth that polar survival required heavy industrial machinery. Decades later, modern structural engineers, thermodynamic researchers, and aerospace designers would study the catenary geometry, cold sump fluid dynamics, and passive thermal buffering of the Inuit snow dome. The principles perfected by Auka and his ancestors would go on to inspire modern energy-efficient architecture, extreme environment shelters, and even the pressurized habitat designs engineered for human survival on the surface of Mars. Ultimately, the story of the snow dome stands as an inspiring monument to human brilliance. It proves that our greatest achievements come not from brute force, heavy industry, or expensive technology, but from observation, humility, and the timeless ability of the human mind to find warmth and life in the coldest corners of the earth.